Okay, as promised, here's a video just to debrief this exam question. We attempted it earlier today. Okay, it gives you a little bit of background here to the circuit, and here's the meat of the question. The transistor has a current gain of 500, and so the input voltage Vin is 5.2 volts, so Vin is 5.2 volts, and the transistor is just saturated, so just at the point of saturation. Determine the base current. Well, we already know the gain, which is 500. We know the current here, and if you remember, the gain equals the collector current over the base current. So if we want to calculate the base current, let's just switch those two things around, the gain and the base. So base current, so the base current is now going to equal the collector current over the gain. So the base current equals the collector current over the gain. The collector current is 1.5 amps, 1.5 over the gain of 500. Okay, so absolutely free to use your calculator. Why not? 1.5 divided by 500 equals 3 times 10 to the minus 3. 3 times 10 to the minus 3 amps, but we know that that is 3 milliamps. Okay, so that's the first answer. The value of the base resistor RB. Okay, so hopefully you remember that there's going to be a voltage drop. This is the base emitter, so VBE. I don't have enough room to write it in there, but VBE is going to be 0.7 volts, and we know that this is 5.2 volts. So this point here is 5.2 volts above ground. We're going to drop 0.7 volts there. So if we then calculate 5.2 minus 0.7, we'll have the voltage drop across there. And knowing the voltage and knowing the resistance, we'll be able to, knowing the voltage and knowing the current, because we know the current remember is 3 milliamps going through there. So we'll be able to calculate the value of the base resistor. So let's do that. So the base resistor RB equals the voltage, which is 5.2 minus 0.7, because that's the voltage potential difference across the resistor. And then we're going to divide that by the known current, which is 3 milliamps, which is 3 times 10 to the minus 3, equals 5.2, and let's just make it like that. So let's go 5.2 minus 0.7 over 3 times 10 to the minus 3 equals 1500. 1500 ohms, in other words 1.5 kilo ohms. Okay, we're getting somewhere now. There is concern that the circuit will not function correctly due to transistor input loading the light sensing subsystem. Yeah, sure, if you remember, if we just cut out all of that, this voltage here will be the open circuit voltage, so no loading on it because it's just these two resistors. But as soon as we actually have a load, then you're going to have this resistor in parallel with the load here as well. Sometimes not a good thing. So that's why there's a concern. The Thevenin equivalent circuit for the light sensing subsystem at an illumination level of 100 lux is shown connected to the transistor input Rn. Okay, so the Thevenin equivalent circuit will be calculated without any of the load. So it's going to be just this thing. Now let's just have a quick refresher. So don't need to do this bit for the exam, but for the exam question, but I just want to remind you. So let's say you've got 12 volts here, 0 volts here, got a couple of resistors here, and you have no load. Okay, so we're going to cut out all of that there. So you've got no load, so that is the VOC, the open circuit voltage. It's open, there's nothing connected in between there and there. Okay, so first of all you work out the VOC, and then what you do is 12 volts, 0 volts. If you already know all this, you can always just skip ahead. Right, okay, so we're going to short circuit it. So ISC, I short circuit. In other words, all the current's going to go around that away, so effectively that's not even there. Okay, so once we know the VOC and we know the ISC, then we can calculate Thevenin equivalent. So R Thevenin, or RO if you want to write it like that. So R equals VOC over ISC. That's the important formula. Now if you notice that there's we're not considering any of this stuff. We're not considering any of this stuff, so all of this is excluded from the calculation for sorry, excuse me, for Thevenin. So they've got this equivalent circuit here. So this resistive load here, sorry, excuse me, that's going to simulate all of this stuff here, RB, and also the diode drop there, or the equivalent to a diode drop. Let me just see if I can grab the next part of the question, and I'll have it somewhere, hopefully. There we go. Okay, so use the equivalent circuit to show by calculation whether a transistor is saturated at 100 lux. Now we know that the transistor is just saturated at 5.2 volts, and we also recall that we know the base current there. So we know the base current is going to be 3 milliamps there. Okay, so we also know, if we know the current going through this, we also can calculate the voltage drop across this. And because E equals IR, and you know the current 3 milliamps, so that's going to be 3 times 10 to the minus 3. You know the resistance, which is 1.1 times 10 to the 3. So in other words, that's going to be, you can cancel out those times 10 to minus 3 and times 10 to the 3. So you can then just work out the voltage is 3.3 volts there. By the way, these calculations will probably be better shown up there. So you know that the voltage drop here is going to be 3.3 volts. Because we know the voltage there is 3.3 volts, and we know that the open circuit voltage was 8.6 volts, then hopefully you can understand what the voltage must be here. And I think they give you a hint somewhere. Hint, you need to consider whether new voltage Vin is sufficient to saturate the transistor. Now we know that the input voltage Vin was sufficient when it reached 5.2. Well, in this particular case we've got 8.6 volts. 8.6 volts, we're going to drop, what did you say, 3.3? Okay, so hopefully you can see that is going to leave us with 5.3 volts. So that's the new Vin. Okay, 5.3 volts, and we found that the transistor was saturated at 5.2. So if we go greater than 5.2, which this is, it will be saturated. What do you have to assertion? Whether the transistor is saturated, okay, therefore is saturated. Let's just make it very clear. Hopefully that makes it very clear anyway. Okay, the system design is improved by adding a comparator subsystem. What we've got to do now, complete the circuit diagram for the system by adding the light sensing subsystem, the components required to provide a reference voltage subsystem, and a facility for adjusting the light level. Adjusting, that's going to be important, so the reference is going to need to be adjustable. I think it came on when light level fell, yeah, when light level fell. So what I normally like to do, just do a couple of fixed value resistors like this, and then think for a moment. Let's just go in here. Now LDR will have an increased resistance in dark light conditions, so in other words, with increased resistance, increased voltage drop. So this is the appropriate place to put it, because when it gets dark, this resistance is going to get bigger, the voltage drop across this is going to get bigger, and then that goes to non-inverting input. So we got that one right. We need a reference voltage as well. Normal thing is to put like a couple of fixed value resistors in, which then can give a reference voltage, being the potential divider, but because it's got to be adjustable, let's go for a potentiometer. And let's take the output. That potentiometer goes around a little bit horrible there. Didn't really need that dot, I don't know why I did that, but I suppose it does show that that joins up there. That's our reference voltage. That's it. Okay, job done. I hope that was useful to you. If you got stuck, I know that this one caused you some problems. Do look back in your notes for the Thevenin equivalent circuits. I almost guarantee you when I set up the exam, the progress test that we're going to have this Wednesday, you're going to have them in like this. Okay, strong hint there, so I hope you're watching. Thanks, goodbye.